if two events are dependent, then the probability of A occurring affects the probability that B will occur. You have to take that into consideration in getting the two or more fractions that you're going to multiply together. Now you have some new notation here. This vertical line, you read that the probability of B, given that vertical line is given that A has already happened. For example, the probability that the second marble is going to be blue, given that I've already taken one blue marble out of the bag. So the formal multiplication rule says if you want the probability of A and B, you find the probabilities independently of each other and then multiply them together. Just multiply them together instead of add them. But if A and B are dependent, then this vertical bar, I don't know why these two vertical bars got scooched in the wrong place. They're supposed to be here and here. Just put those vertical lines in on your notes. For the second probability, you have to take into account what happened on the first trial. That's the big scary way of just saying, make sure you're checking to see that what happened on the first trial, or how what happened on the first trial affects what's going to happen on the second trial. Sometimes it doesn't affect them at all, and those events are independent. But if they are dependent, you have to take that into consideration. The intuitive multiplication rule says the very same thing, just in words instead of symbols. All right, so let's practice finding whether two events are independent and then find the probability of A and B. That's the probability that both things happen. A happens on the first trial, B happens on the second trial. Now, try to picture what's going on. I have a calendar in number 1. I have a calendar. I'm going to rip a page out. What's the probability that if I just close my eyes and rip out a page, what's the probability that the page I just happened to get is July? Yeah, disregard all the extraneous pages in the calendar. 12 months, only one of them is July. So the probability that you randomly pick out July is 1 out of 12. Let me see where I can write that down. Probability of July is 1 out of 12. Now I'm going to close my eyes again, rip out another page, and see if it's November. Would those two events be dependent or independent? Tell me why you're saying dependent. You've already ripped out a page. There are no longer 12 pages in the calendar. So if you've already ripped out one page, that's the probability of November. Given that you've already ripped out July, the calendar started with how many pages? 12, and after you ripped out one, it had 11. So what's the probability you're going to get November on your second rip? 1 out of 11. Because those two events are dependent, that's why the probability in the B part is not the same thing as the probability in the A part. Now that I have calculated these two probabilities separately, how do I find the probability of A and B? You multiply them. If it was A or B, you'd add them. But since it's A and B, it's 1 over 12 times 1 over 11, or 1 over 132. Wouldn't be very often if you had 1,000,000 calendars and you closed your eyes and ripped out 2 pages. It wouldn't be very frequently that the first one just happened to be July and the second one just happened to be November. What is that probability if you round it to 3 decimals for me? No. That wouldn't be 0.132 unless you were 0.008. You actually have to divide. What you're thinking is if you had 132 divided by 1,000, it would be 0.132. And that's not what this is. This is 1 divided by 132. Anybody second that? Okay. All right. Thank you. What about number 2? If event A is, it's a girl, does that affect at all what you expect to be the gender of the second child? No. Those 2 events are independent. The first kid, the probability of a girl is what? You could say 0.5 or a half, whichever is your favorite. And then the probability of the second child being a girl, given that the first child was a girl, is what? Still a half. Because those 2 events are independent of each other. So how do you find the probability of the first child being a girl and the second child being a girl? 1/2 times 1/2. That means if you looked at 1,000 families that had 2 children, about 25% of them, both kids would be girls. What about my case? I have 3 daughters. If I looked at all the 3 children families in the U.S., what's the probability that if I randomly selected one of those, they would all 3 be girls? How would I get that probability? I think you know what? I don't know the decimal in my head, but I can tell you the fraction very quickly. Well, if I just had 1 more child, what would I just multiply by 1 more half? The probability of the third child would also be a half, and a half times a half times a half is an eighth. That's actually 0.125 or 12.5% of 3 children families would have all girls. All right. Finish that. What about the lottery? The lottery, I'm gonna be the lovely lottery lady, and I'm gonna draw ping pong balls out of, this is a 4-digit lottery, so I've got 4 buckets, 4 rotating things. I can't think of bins, 4 rotating bins, and I'm gonna draw a number out of each one. Well, the first bin has the number 0 through 9. Second bin has 0 through 9. So do the third and fourth. How many numbers are in each bin? 10, because don't forget 0. There are 10 numbers in each bin. This is not worded as simply as it could be, but let me just simplify it for you. Does what I draw on the second draw in any way depend on what I pulled out of the first bucket? No, they're definitely independent. What is the probability that that first ping pong ball is going to match the number on my lotto ticket? 1 out of 10. There are 10 balls in the first bin. I'm going to draw out one of them. Only one of them's a winner. So the probability that the first I'm just going to say first number is a winner because that's the shortcut way of saying all the stuff that's typed. Probability the first one is a winner is 1 out of 10. What's the probability that the second digit is a winner? Because that doesn't depend on what I drew out of the first bucket. It's still 1 out of 10. So what is the probability that 1 wins and 2 wins? I'm not stating exactly what I mean just because it saves me a minute writing, and minutes are important right now. Seconds are important. Multiply them because it's first and second are both correct. Let's say that we have 100 people gathered together in a gymnasium to watch a drawing for a $10 million prize. 100 people went in together, bought the ticket. They're all glued to the TV at the same time. After the first number is pulled, how many of them go, woohoo? One out of 10. So if there are 100 in the room, how many people say, woohoo? 10. How many people walk away? The other 90. All right, now there are only 10 people in the room. When the second number is drawn out, how many people say, woohoo? Yeah, there are only 10 people in the room, so only one is excited at that point. The other 9 walk away. This would be bad if it was a pick 4 lottery because we still have 2 more ping pong balls to go. Just to show you why it's so hard to win the lottery, let's do the probability of all 4 numbers being correct or being the winning number. How would you get that? There would have had to have been 10,000 people go in on a ticket for any of them to have a realistic chance of winning. And if you want to split, I'd split $10 million with 10,000 people. That would still make me happy. But unfortunately, I don't think I have 10,000 friends. I would have to start a Facebook. And I'm not going to. Unless my grandchildren someday will not communicate with me any other way, I'm never going to have a Facebook. All right. Any questions on that one? Okie doke. Next. We're making much better time than my Monday, Wednesday class when we did this. We didn't get through all of our examples in that one. Number 4, very, very real life. In industry, quality control is important. If you don't make a quality product, you are going to go out of business. Now, if you're making, let's say, bolts that hold really important things together, bridges maybe, you probably make 10,000 bolts a day. And that bolt has to be the exact size or pretty darn close to it to keep that bridge standing. It's not okay to have a too big bolt. You're going to have to throw them all in the river, and then you're going to get fired for wasting money and polluting the river too. They can't be too small or it won't fit snugly in the hole it's supposed to fit in. But you're making 10,000 bolts a day. Can you check all 10,000 bolts with those little calipers that measure how the diameter. No, you'd have to hire 5 more people just to measure all the bolts. So you take a sample. You look in the bucket of 10,000 bolts, you reach in and you grab out 4. And you say, if these 4 are okay, I'm going to assume today's batch is okay. If all 4 are good, I'm going to say, yep, today's batch is off for shipment. If one of those 4 is bad, then I'm going to say chunk today's. Or maybe let's go back and test each one. I'm going to have to do something though. All right, so that's called batch testing. The entire batch is accepted if every item in the sample is okay. Now, here we're talking about airport baggage scales. We know that out of 810, 102 are defective. We want to find the probability that if we reach in, grab 4 of those scales, what's the probability that we're going to accept the whole batch? Just looking at these numbers, do you think we should accept the whole batch? That's about 12% of them bad. Would my sample of size 4 catch that? That's the question. And rather than just saying my gut says no or my gut says yes, let's find the probability that if we reach in and grab 4, none of them are going to be bad. That's what we're looking for. Let's see. If 4 of the scales are randomly selected and tested, what's the probability that the entire batch will be accepted? Tell me how to calculate the probability that the first one I draw out is going to be good. No? What's the probability that the first scale I test is going to be fine? 1. No, there are more than just one bad one in the batch. That would give me the probability that I find a bad one, but I ask for the probability that I find a good one. You see how important it's going to be to read carefully here? If I ask for a probability that one is accepted and you say 102 divided by 810, you got the right answer to the wrong question. You just told me what's the probability that one is bad. So how are you going to get the probability that one is good? That would give you the number of good ones. 102 defective means there are 708 acceptable. And so the probability that the first, I'm just going to say probability of acceptable, if you're writing with a pencil, put a big old 4 on that thing I scratched out. That's what we're actually trying to find, not just the probability that the first is acceptable, but the probability that all 4 are acceptable. Well, in a long conversation, we just figured out that the probability that the first is acceptable is 708 out of 810. That's a pretty high probability that the first one's going to be good. If we don't put that one back in, if we draw out an acceptable and don't put it back in, what's the probability that the next one's going to be acceptable? 707 out of, now there are only 809. And if that one's acceptable and I don't put it back, what's the probability that the next one is acceptable? And the last one? Probability that the last one's acceptable? Yes. Would you call multiplying those 4 numbers cumbersome? it's kind of there's a fine line on what's cumbersome and what's not cumbersome. I can't give you a magic rule on that. I promise that I'll try to make the one on the test obviously cumbersome or obviously not cumbersome. That looks pretty cumbersome to me. It's not hard to multiply 2 fractions, maybe not even 3 fractions, but 4 is getting on my nerves. So what could we do to use the 5% guideline? First thing I'd have to check is 8 less than, not 8, I'm not drawing 8, I'm drawing 4. Something's going on with my 4s. Is 4 less than 5% of the 810? Is it? Yeah, it's way less. And because it's way less, I can say the probability of 4 acceptable what does the 5% rule say that I can do? No. Five percent guideline says, well, just play like you're putting it back. And that way, all 4 draws, the probability of acceptable would be what? What was it originally? 708 over 810. If you use the 5% guideline, you just multiply that times itself 4 times, or even easier on the calculator, 708 divided by 810 to the 4th power. That's much easier to enter on the calculator. But you do have to have this fraction in parentheses before you raise it to the 4th power. Somebody have that for me? 0.584? Anybody second that? A third? Okay, I got several nods. 0.584. That means if I use this method, if I only use a sample size of 4, 58, almost 60% of the time, I'm going to say, yep, today's batch is good. I only drew out 4. All 4 were good. Yep, today's batch is good. But we know today's batch is not really that great. So that tells me I'm going to need to draw out more than 4. Maybe if I drew out 8 and all 8 were good, maybe that would be sufficient. But this pick 4 method is not going to catch how many days we really have an unacceptable number of defective scales. So I would say answer to that second question is no.